I will speak about first a brief discussion of the main results of the intercomparison campaigns that have been celebrated during the last 4 years. And after that, I will discuss also some instrumental characterization issues, more or less the same as was discussed by Ilias now, about the time neutral density filters and also some method to correct, some empirical method to correct the stray light on single Brewers. Okay, so I will focus on the period of time from 2009 to 2013, 9 brewer intercomparison campaigns during this period, with 35 instruments from 13 countries. All of these campaigns were celebrated with the support of some European Space Agency CEO's Intercal project. An overview of the main result of these campaigns, which I think could be quite interesting, are referred to the results of comparison with the standard instrument or the reference instrument, and also because of the high number of instruments participating in these campaigns, I think that we have a good opportunity to assess the status of the Brewer network, the European Brewer network. So we see that around 2/3 of the reported data sets show daily ozone deviations to the reference instrument within ±1%. I don't know how. ¿Cómo se enciende el láser, Alberto? Okay. So the first plot, it refers to the initial status of the instrument. We process the data during the blind days when the instrument comes to the campaign, and we process the ozone data using the provided configuration file by the Brewer operator. So we see here the ozone deviation frequencies for all of the ozone data sets. We process here around 69 data sets. And in the plot below, we see the result after the final calibration constants were applied, what we call the final days. Okay, as concerns to the blind days, we see that around 2/3 of the instruments were within ±1%, and just around half of the instruments were within the 0.5% as compared to the reference instruments. And after the final calibration constants were applied, we get a very good result, a good comparison with the reference standard. I have to say that these numbers, these statistics, refers to the best of both ozone data represented with or without a standard lamp correction. Sometimes In principle, it's not easy to know in advance if the standard lab correction will work or not. The only way to be sure of this is to compare your ozone data with another ozone data set, for example, from some reference instrument or from satellite. Because as I show in these plots, sometimes it works. For example, in this case, the blue plots are no standard lamp corrected, and the red ones are standard lamp corrected. In this case, the standard lamp correction works quite well. But in this other case, the standard lamp correction doesn't work at all. So, okay, now I will continue with some topics. I will start with the time constant. And what we see in this plot is the difference between the calculated dead time constants and the operational value. It is also remarkable that the tolerance range used to be 2 nanoseconds, and we see in the plot that a large number of cases show the time deviations higher than 2 nanoseconds. In some cases, it's really large, like in this case. A large number of instruments show that time deviation of the order of 5 nanoseconds. And this issue also affects to some standard instruments. For example, the RBCC-E absolute standard instrument, the 157, or also the iOS 17 shows also differences. So how does this affect to ozone retrievals? Okay, if we assume Poisson statistics, then we correct the observed count rate as following this equation. So the effect of that time will increase with light intensity reaching the detector, the PMT tube. We see in this plot that the effect of that time is quite different for double than for single brewers. In both cases, we have in this plot here, the gross plot refers to a double brewer, and this other plot refers to the single brewer. The different colors are for different neutral density filters. Red for filter 0, green, blue, and the other for filter 3, and so on. So you see that in both cases, for double and for single, we are processing ozone data with to the times that are different 5 units between them. For example, for double brewer, we have 28 and 32 the time, and the difference between both is very, very small, less than 0.5. And in the case of a single brewer, the same difference in the time, 5 units, leads to a quite big difference in ozone. It could be as large as 2%, for example. And it's important also to know to notice that the biggest difference are when the instruments change the neutral density filter. We see, for example, in this plot that we are using the neutral density filter 0, and then we change to the neutral density filter 1 and 2 and 3. And when changing the neutral density filter, we we see a change in the intensity of light, and according to this, we see the change in ozone also. So we can deduce from this that the depth time will modify the overall neutral density filter's performance. So how we determine the time? First, two measurements regimes are possible for accounting system, parallelizable and non-parallelizable. Brewer software assumes the first to be valid, which is valid for Poisson statistics. And normally both regimes will be equivalent for low count, less than 2 million count, let's say. And we calculate, or the Brewer calculate the depth time from the standard lamp, internal halogen lamp. Maybe we are missing something because of low standard lamp intensities. So that's why we wanted to test if increasing the light intensity we will get different results or not. So we modified the DS routine to make measurements on all slits, on slit 7 and 2 and 4. And we perform the same calculus as the Brewer does to calculate the time. And this is the result. We show the result in this plot. We see here the squares, the yellow and black squares refer to the normal DT average file. In black, we have the high intensity, and in yellow, the low intensity, the time. And then we have the dots. The dots plot are the results that we obtained from this set, from the modified DS routine to calculate the dead time. And we see exactly the same results, no difference between both methods. And this is for Brewer 157. And this is the dead time calculated against versus time, and this is the same but versus intensity of light at the slit 7. So we see that the best results are for count regimes of about 1 million of count, and for low counts we have very noisy results, quite similar to the low intensity results of the standard lamp test, the dead time calculated with the standard lamp, I mean. So it seems like the intensity of light have nothing to do with the results that we obtain, at least in this case, with this Brewer. So we can ask also if maybe the method that we employ to invert the previous equation, this one, is valid or not. Several methods are possible. We have some iteration method in Brewer software, but we can apply also, for example, the Newton method, but no large changes are expected between different methods. So what the facts are? The facts, for example, this is quite common. We have a Brewer is working with us with some operative value. In this case is 41 nanoseconds, but we measure a value which is quite different. In this case is 35 units, 35 nanoseconds. So what value should we use? Which one of them is correct? it's not just as simple as updating the depth time to the calculated value, and that's all. In this plot here, I have, this plot refers to the ozone deviation of this Brewer, the 70, compared to a reference, in this case, the 183. And I have used different configurations in both plots. In this case, I use 41 nanoseconds for that time, and in this case, 35 nanoseconds for the time. And we see that updating the depth time, we can improve the neutral density performance. I have highlighted the chaining filters with red circles in both cases. And for example, I have made some zoom of this case when the instrument changed from neutral density 1 to neutral density 2. And we see that we have some difference between ozone measurements taken with both filters, which can be as high as around 1%. And if we apply the calculated depth time constants, then we can improve the ozone measurements calculated with both filters. We have improved the linearity of the instrument here, but then we get very bad results for filter 3. First, we see that maybe we have to apply some correction to filter because of this change in ozone measurements. And the most important is this kind of slope that is induced after updating the depth time. And we see here no slope at all, but here we can see some slope in ozone measurements. So I think that the better possibility will be to update the PMT high voltage in cases like this. We see that the time is decreasing maybe because of PMT aging, or I don't know. And analyze also the way that Brewer software manages the neutral density filters. Next, I will briefly speak about the neutral density filters. The standard Brewer software operates under the assumption that neutral density filters are neutral. That means that it attenuates all wavelengths equally. But in case we have neutral density filters spectrally different, then we will have to deal with different ETCs for each of them. And I show this in this plot. This is the Brewer 37. And we see that filter 3 is non-neutral. We can see this step in ozone measurements when changing from filter 2 to filter 3. And after we correct the issue, then we get a nice result in the comparison against the reference Brewer 183. So several methods are possible to determine the neutral density filter ETC correction. A good review of this topic can be found in this web page. This is for some workshop, Brewer workshop in Beijing in 2011. But to summarize, we can try to determine the neutral density filter non-neutrality by means of the FI routine or AT routines, or we can use some reference instrument to calculate the different ETCs for the different filters, or we can use also absolute calibration, I mean Langley plots, to accomplish for the same. I will focus on items 1 and 2. So the way we analyze the ozone data to see or to check the filter's performance is to compare ozone data that are taken with different filters, but I mean when immediately after changing the filter. In this way, we can analyze both the neutral filter's performance and the dead time setting, the dead time constant setting. This method does not depend on accurate of the ETC constants, nor on comparison with a reference instrument, because it's internally, it is performed just with the instrument's data. But you need to process enough ozone data in order to achieve reliable results. I show two examples here in this plot, which I showed this kind of analysis for Brewer 157, and in this case, the problem is with the time we have. The operative dead time is 32, and we calculate 28, but we see that no significant differences between both the times. And in this other case, I show the case of an instrument we have that have some neutral density filter non-neutral, and in this case the filter 3. And we see in red, the red box plots are before applying the filter correction, and in green box plots are after applying the filter correction. So this kind of analysis allows us to detect problems in some instrumental for example, in the time or in neutral density filters. So how to correct this effect in filters? What we do is just applying the standard one parameter ETC transfer for the filters affected by the problem. In this case, I am speaking of instrument 37, which shows some problems in neutral density filter 3. So what we do is to calibrate first the instrument just with filter 3, and we obtain an ETC of 3115, and then we remove the filter 3 and we use the rest of filters, and we obtain 3104. So from this we deduce a filter correction of about 10. And after this, we just correct the total ozone in a similar way as we do with the standard lamp correction. And this is what I show here. In this way, we achieve very good results. For example, we apply this 10 factor to 37, and this is before and after. And finally, I will speak briefly about some single Brewer stray light rejection method. We have developed a method to correct this stray light. It's an empirical method, and it's based completely on comparison with a reference instrument. In the first plot, we see clearly the stray light issue in this Mark IV Brewer. So this procedure is based on some sauna results, and what we do is simply apply some fitting, some curve fitting to the total pairs of ETC ozone slant path values that we obtain after applying the one parameter ETC transfer method. Then we try to fit all these points with a power law in this way. And this is the ETC, and this is the correction factor. And the algorithms to correct the stray light seems quite simple to apply. First, we have to compute the total ozone, as usual. Then we apply the empirical relation to obtain the ETC for the whole ozone slant range. And finally, we can use the corrected ETC to obtain the stray light corrected ozone, total ozone. We have to iterate this method because first we obtain the relation is obtained during the intercomparison, during the comparison with some reference instrument. So here we are using the total ozone from the reference, but at the station, when the instrument is operational in the station, because of the stray light, it will measure a different ozone, a very lower ozone. So we have to iterate the process, but we found that by doing so twice will be enough to achieve very good results, which is the red plots here. The green line is the original data without correcting for a stray light, and then the blue dots corresponds to the first iteration, and the red one to the second iteration. And after that, this method should work fine enough so as to achieve the required precision plus minus 1% on Brewer total ozone. We have tested this method in the last intercomparison campaign in Herenosillo 2013, and we have observed a very good results. We can see here before the comparison of each single brewer participating in the campaign against the reference 23083. This is before applying the stray light correction, and this is after applying the stray light correction. And we have also confirmed with Brewer 37 that this correction can be applied during the time. We have applied the same correction to different ozone data sets since 2009 until 2013, and we get very nice results. So, as conclusions, around 2/3 of the reported data sets show daily ozone deviations to the reference instruments within plus minus 1%. Comparison with other ozone data sets is necessary to know if the standard lamp test properly track changes in the instrument response. Otherwise, you will have to wait until the next intercomparison. The time setting has not the same effect in single as in double brewers. Variations of around 5 nanoseconds result in maximum ozone deviation up to 2% for a single brewer. Maybe the accepted 2 nanoseconds tolerance range in that time would be too restrictive for doubles. Maybe it will be better to use 3 nanoseconds or maybe 4. For non-neutral density filters, we will have to deal with different ETCs for each of them. we use the standard one-parameter ETC transfer method to calculate the corresponding ETC correction. Overall, neutral density filters performance is mostly affected by dead time constant. An empirical corrective method for single Brewer stray light has been developed, which seems easy to implement for real-time ozone correction. And this should work fine enough so as to achieve the required precision ±1% on Brewer column ozone. And I wish to dedicate this short presentation to the memory of Mr. Ángel Miguel Bonet, which has recently left us. And thank you.
When you showed the plots of what happens when you, the comparison between two brewers when you applied SL correction and then when you didn't. And if you find
when I apply the stray light or?
No, the standard lamp correction.
The standard lamp, okay. It's the second slide, so.
No, it was way back.
It's here, okay.
That one, yeah. So, where you say sometimes it works, sometimes it doesn't, but it's not actually clear how you've done that. Have you taken the standard lamp correction off both instruments to compare? And you got the blue plot is when you don't apply standard lamp correction.
Yeah.
Well, is that without the standard lamp correction on both instruments that you're comparing, or just one of them?
No, it's just the comparison with the reference instrument. I am comparing one instrument with another one, the reference instrument, and I have two data sets for each of them without the standard lamp correction, which are the blue plots.
So,
and then
so both the reference and the other one have not got.
The reference is without the standard lamp.
Usually we don't use standard lamp correction on the reference because it's very stable.
Yeah,
okay,
we don't apply
right. So there's no standard lamp correction on the in either plot.
The reference instrument is the same. It's the same for both plots.
Okay.
No change.
What are the grade points?
The grade points in this case is all the instruments during the campaign.
Okay.
It's a good view of the initial status of the instruments. Grade points are all the instruments before calibrating them. So this is what we have before applying the final calibration constants.
And
yes?
one other question on a different subject from that, which I guess is for you and for Ilias.
Yeah.
When you actually do the studies on the dead time, do you actually check the photomultiplier tube first for the HT and that it's working in the right place and everything?
It's supposed to have been checked, so we haven't done it exactly before the measurement.
So basically you're doing the experiments on the dead time and you have no idea what the state of the...
No. We had a problem with the photomultiplier, and that seemed... I haven't got the plot here. I initially had it, but I hadn't got time. The photomultiplier condition was affecting in a bad way the dead time. When we checked the photomultiplier, we changed the discrimination time. We checked the H3 test, and it was about 1 month before the test. Then the dead time immediately went to the correct place. So, yeah, I believe that we had no photomultiplier problem for our results.
Well, how do you know which is the correct place?
Well, you can't. I don't know. I can't. Yeah, correct place. I don't know a way to decide which is the correct place. So.
Bolodi, I have a question. No?
Since this I just want to comment. Since this graph is here,
So, sorry, Volodya.
Yeah. For 214, you show that the correction that you tried to apply for the standard lamp ratio changes did not work. That's clear. But has anybody verified that the reference standard lamp ratio is correct?
Yeah, but sometimes this is important to...
No. Okay, so I mean, this is not very good example then, period.
Yeah, you're right, but the good of this kind of plots is to stress that, because sometimes some brewer operator give you a standard lamp reference that is wrong, or maybe they change the ATC but doesn't change the standard lamp R6 reference value.
Right, but this is more towards the reference value rather than how well it tracks the changes of the instrument.
Yeah, you're right.
And I think this is important for people to know, because it's completely different.
It's completely different, yes. I agree.
Yes, yeah, that's different. Yes, that is
yeah, but in some cases the standard lamp doesn't track the. No, not this case. But the important is to be sure that you are using a good R6 reference value.
Yeah. Okay. Now, about the dead time, I have several comments. First, I would like to emphasize that everybody appreciates probably that the high intensity, the more correction for the dead time. But equally important to remember that the larger the value of the dead time, the more correction you end up having. So the error in the dead time is more important at higher values of the dead time. And the instruments can range, especially with the new Hamamatsu PMT, they can range from 20 nanoseconds to 45 nanoseconds. So depending on where you are, the 5 nanoseconds that you used as an example change will be very different.
Yeah, I'm agree, yes.
In these cases, right? So, and another thing, kind of a continuation of this, one thing that was missing from these plots for the dead time and the neutral density that you showed was that in many instruments, the change in the optical depths for the filters from one to the other exceeds what we believe is the dynamical range of the counting system, including the PMT. So you actually introduce from going, for example, from high attenuation to low attenuation. As soon as you switch, you actually go to extreme high intensity, which normally we do not expect.
You said that you have to use a higher filter before.
No, not necessarily. I would prefer to see filters spaced exactly as they are designed to be at in log 10, it's 0.5. So this is what we expect them to be. And I've seen instruments to have 0.7 spacing and sometimes even larger. And so you cannot find a position of these filters that is good, because at one position you will be having too bright of an intensity, in the other it will be too dim. So this is something that has to be addressed separately before you analyze it, or at least provide information in your analysis so that it is known that it is optimal in that sense. Because some of the problems that you may be seeing is that you just cannot work in the linearity range of the PMT. You know? Yeah.
Okay, almost the issue behavior when it's a part of
One comment is that I see no physical explanation or any physical reason why you should make a statement that the dead time would behave differently on a single or a double. I would believe that it's a lack of really systematic separation of the filter and dead time issues properly. Oh yes, I know there's that difference, but if the dead time model is accurate, then there should be no difference. Yes, the effect of the error will be different, right? Yeah, okay. Right. Then they're going to mix. Oh yeah, differently, yeah. The other point is that I think it's important to understand that the business of measuring the dead time at two different intensities and then seeing that the higher intensity dead time measurement lies nicely within the scatter in the lower intensity measurement is really a validation of the dead time model. And that's quite important because if there's something wrong with the high voltage system, if you're set at the wrong voltage on the photomultiplier or something like that, you can have extraneous effects that go on that can even make it superlinear. And it will not be making proper measurements when you're switching dynamically between the slits. So it's important to do that zero order evaluation that the two are at least consistent and that the uncertainty in the dead time that you measure at high intensity will give results that are within the appropriate error range at the lower intensity, and then you're safe, right? It means the model is close enough.
Okay, thank you.